Hello and welcome to another mathematics video in which we seek to analyse and solve ordinary differential equations. Now here we've got another non-linear circuit and we're asked to find an ODE for it, a non-linear ordinary differential equation that describes this circuit, and solve for the current. Now well, we're going to have a go at solving this circuit, forming a differential equation for it and solving for I. So what we're going to do is we'll use, what should I do? Let's go on to another page. So basically, let's just draw this circuit again. We'll draw it in green. So we've got a voltage here, which is connected to a resistor and a non-linear device, which we'll call Ki squared, and that in turn is wired up to an inductor of magnitude L, an inductor L, and then of course we've got a switch that connects the circuit like that. Now let's use blue. So E, the total voltage is equal to L di by dt plus the voltage of the resistor, which is I times R, plus Ki squared. Okay, and so again, here we have the voltage across the inductor L, the voltage IR across the resistor, and the voltage Ki squared across the non-linear device. Now I'm going to show you the simplest way of solving this equation, and that is to simplify the equation by letting it equal 0. So we want to solve for the system for a 0 total voltage. So what we do now is I'll turn to black ink. We divide throughout the equation by L to get di by dt plus R over L, and I'm going to, and that's got an I there. I'm going to move this Ki squared divided by L to the other side of the equation, so that we have minus K over L I squared. So you might recognize that this is a Bernoulli equation. So this is a Bernoulli equation. So to solve, put, let me see, what do we put? We put V equal to I to the power 1 minus n, right? Well, what is n? Well, from this equation here, n equals 2. That's this indices here. So basically, we just change our nib again, we get v equals I to the power 1 minus 2, which is equal to I to the minus 1. So in other words, v equals 1 over I. And dv equals minus I to the power minus 2 di. So that, or such that, di is equal to I squared, it's actually minus I squared dv. And because from here, I is equal to 1 over v, then di is equal to, well, the I squared can be written as 1 over v squared. So we've got minus 1 over v squared dv. And this implies that di by dt is equal to minus 1 over v squared dv by dt. Now we'll need that. We'll need that because we're going to substitute it in to here. We will need I because we're going to substitute that in for here and for here. So let's go ahead and do that. So first of all, I'm going to cut and paste this. Right, okay, so we know that I is equal to 1 over v, and I squared equals 1 over v squared. Right, make that look more like an I, and that more like an I. And what else do we have? Well, we have di by dt, di by dt is equal to minus 1 over v squared dv by dt. And I'm just going to double check that again so that we don't get anything wrong. So substituting in to, well, we'll call this equation 1, right? We get minus 1 over v squared dv by dt plus r over L, and then we've got times 1 over v, and that's equal to minus k over L times I squared, which is 1 over v squared. Right? So now multiplying both sides by minus 1 over v squared, we get dv by dt minus r over L times v, because a v squared divided by v is just v, and that's equal to minus k over L. Right, we've got a simplified equation. Now let's take equation 2 and add it to a new page, and then we can hopefully solve it. So let's go to green ink. So we want an integrating factor to solve this equation, and that's of the form e to the minus r over L times the integral of dt, which comes out to be equal to e to the minus r over L t. So multiplying both sides of equation 2 by e to the minus RL over t, multiplying both sides of equation 2 by minus r divided by L times t, then we get the following. Minus r over L v e. Ooh, I'm going to write that in green, aren't we? So that's e to the minus r over L times t equals minus, let's be consistent with what we're doing. Right, so minus k over L, and green ink again, e to the minus r over L t. And we'll call that equation 3. So now you should be familiar with these kind of equations with integrating factors. We can rewrite the left-hand side as d by dt of e to the minus r over L times t times v, and that's equal to minus k over L e to the minus r over L t. Now, integrating both sides, we get e to the minus r over L v equal to minus k over L. Let me just get rid of the stylus. So e to the minus r over L times v is equal to minus kl divided by, well, we're integrating e to the minus r over lt. So this becomes minus r over L in the denominator. We'll just write it like that. And then we're left with an e to the minus r over L times t there, plus a constant c. Right. Now let's bring the stylus back and cut and paste. I think we'll have to abort that. Right. Is that good enough for our purposes? Yeah, I think so. So let's just, there we are, R T. Right, okay. So I think I've made a slight error there. So let's go back to the previous page. So as you can see, I have made an error. That should not be a V there. That should be a T, and the V should be there. So let's go to the next page and convert that into a T. Sorry about the mistakes. So this simplifies to give e to the minus r over lt times v equal to, well, two negatives are a positive, and we've got k divided by L divided by R divided by L. So that's like k divided by L divided by R divided by L. But what we do there is invert, turn it into a multiplication, and invert the bottom fraction. And that's e to the minus r over lt plus c. So we've got, well, we can cancel the L's, and we're left with e to the minus r over lt times v equals k over r, e to the minus r over lt, make that look more like a minus sign, plus c. And I haven't given these equation labels, have I? So let's call that equation 4. So this equation 5, equation 6, equation 7. I'm writing a bit fast here. But anyway, so we'll cut and paste that equation 7 and go on to a new page. Right, so dividing throughout by e to minus r over lt, we get v equal to k over r plus c e, this time to the rl over t. Right, it's akin to actually multiplying both sides of the equation by e to the r over lt. So these two cancel, this cancels with this, and hence we get the equation that we're going to label equation 8. Hence we get equation 8. So now we know that v equals 1 over I. Is that right? Let's have a look. Yeah, so I equals 1 over v, or v equals 1 over I. So we can write 1 over I is equal to k over r plus c e to the r over l t. That is our equation. Let's make that look more like a decent arrow. So that's our equation 9. Right, so it's quite simple. What we do next, add to new page. That's our R. Right, so inverting both sides, in other words, multiplying both sides by I and dividing both sides by everything on the right-hand side, we then get I equals 1 over k over r. We'll put that in little brackets plus c e to the r over l t. And I'm going to rewrite that. We'll call that equation 10. But we can rewrite that as I equals, well, let's do the denominator first. Multiplying top and bottom by r, we get r on top, and we get a k on its own there, plus c r e to the r over l t. And equation 11 is our answer when E is equal to 0, when we want the total voltage to be equal to 0 from all those components added up. So I hope that you've enjoyed that lecture and that you've got something else of it, and that it's helped you. And until next time, I'll bid you farewell for now. So see you soon. Bye.